All right, so I'm going to be debunking the metric system in this video. This is going to be an interesting thing because most of us think the metric system is really rational. I think it's actually quite irrational. So, people point to the imperial system and they go, "Ah, look at the metric system. It's much better." Yeah, it is better, but the imperial system sucks ass. It's not hard to beat the imperial system. Any 6-year-old kid could make a better system than the imperial system. So, what's wrong with the metric system? What have I got against the metric system? Well, I'm not for the imperial system, but the metric system has a lot of big problems. So the first thing is the scales. We can see a lot of metric units jump by a scale of 10, and a lot of metric units jump by a scale of 1,000. If I go up to a random person on the street and I tell them, a femtometer is smaller than a picometer, by what scale, right? And they say, I don't know, 10, 100, 1,000, I don't know, they wouldn't have any clue. You can't figure it out from the name, okay? So these names aren't necessarily useful. And, some people can say, well, let's take a deca. Deca means 10, right? But, at the same time, we can look at like centa and we would think, well, centa, century, that means 100. Mille, that could mean millennium or maybe a million. It's not too clear, right? That could mean 1,000 or it could mean a million. And in fact, it means one 1,000th or one, these are fractional. So how would you know that a centimeter is like a fraction of a meter rather than like 100 meters, for example, right? That's not rational. You can't figure out the quantity by the name. And the second thing is, even if you can, you still have to convert the name into the quantity, right? So it's very inefficient, and I'm going to prove to you it's inefficient. Okay, I'm not just saying that. Your job right now is I want you to convert 1 picometer into a gigameter. Tell me how many picometers is in a gigameter. All right, do it. Use the chart. This is with the chart. Normally, you don't have this chart. I'm even giving you this conversion chart right here. See how long it takes you. I bet you it's going to take you like, if you're good at math, probably 30, 40 seconds. And if you're not so good at math, it might take you 10 minutes, Not so easy, all right? Okay, so how does the deca scale system work? It's really damn simple, okay? So everything is 10 times larger than the previous unit. So scale 1 is 10 times larger than scale 0. Scale 2 is 10 times larger than scale 1, right? And then when we start going to decimal numbers, we get our negative scales, all right? Now, this is much, much, much more intuitive and simple, all right? So, for example, if I ask you, is scale 5 bigger or smaller than scale 3? Duh, obviously scale 5 is bigger. And if you want to figure out the exact size of the scale in layman's terms, it's very easy. Just the scale number is the amount of zeros in the number, all right? So, for example, scale number 4, we have 4 zeros, right? If we go to scale -6, how many zeros are there going to be? 1, 2, 3, 4, 5, 6 zeros, right? So that's the simple layman's way. And then for the scientist, the conversion is unbelievably easy. So, for example, all right, so let's just use it in scientific terms here. Let's say we want to find the difference between scale 1 and scale 5, right? Well, that's super freaking easy. The difference is 4, right? 5 minus 1 is 4. So we go to scale 4, and we know that scale 1 is 10,000 times smaller than scale 5. That's simple. Or if you want to just look at it in mathematical terms, it's going to be 10 to the power of 4 times smaller, right? Look how fast we can do these conversions, okay? So let's say we want to jump from scale -6 up to scale, 3, right? What's the difference between -6 and 3? Well, that's a difference of 9. So we just look at scale 9, and that would be the difference. Or we could just say 10 to the power of 9. That's simple. We can do the conversion in 3 seconds. Any mathematician or scientist can use the scalar system and convert units in just a matter of seconds without any calculator. You can just do it all in your head. It's that simple. Now, the most irrational thing about the metric system is when we actually do math in the metric system, we're simply converting it to the deca scale system, and then we're doing the math. So why don't we just use the deca scale system instead? What's the point of having all these other names, So whenever we do a calculation in metric, the first thing a scientist is doing is he's converting it to the deca scale system, and then he has to convert it back to the metric system to get the name he wants, right? So why not just leave it in this mathematical notation? It's a lot more logical. It's a lot more intuitive. It's just a lot better, I think. And so much of the language we use is counterintuitive or silly. Like here's an example. Okay, so we have these three red lines here, and I gave the AI my names for them. Okay, so my names are a circle stab, a circle skim, and a circle spoke. And the AI immediately correctly guessed which is which. This is the circle. B is the circle stab because it looks like a circle getting stabbed with like a knife. The circle skim is C, right? That's the line is skimming the edge of the circle, and the circle spoke is A because it looks like a spoke, in a bike wheel or something, right? So these are much more intuitive names. And I think when you make things like intuitive and logical, people have way more working memory they can use to actually think about ideas. And they're using way less of their brain power to just like try to understand what all these names mean. Like the mathematical names for these are a chord, a secant, and a tangent. Could a child guess which is which? I really doubt it. They might get the chord right, but there's no way they'd know which is the tangent or secant, right? And all these things, there's so many ways we can make things logical. Like take a triangle, okay? So why do we call the long side a hypotenuse? Why don't we just call it a tri-long side, right? Tri-long side. A 2-year-old kid can figure out which is the tri-long side, And another example is in trigonometry. We have sine, cosine, and tangent. And the very first thing people do is they remember this formula, SOHCAHTOA, right? To do the trigonometry. Well, why don't you just make the actual trig functions SOHCAHTOA, right? Why even use the terms sine, cosine, and tangent? Just make the actual function itself SOHCAHTOA. Then you don't have to think, okay, what is sine? Sine is so, right? Why don't we just say so is the actual function? And you don't need the S in that case. You could just call it OA, right? OA is the math function, right? So, there's so many ways we can make the language much more logical, and I think this is a great way to really speed up progress a lot. Anyways, I could talk for years about the jargon in science, and I even have tests on this where I give scientists these arguments written in like all this technical language, and then I give them the same argument written in plain English. And on average, the scientist immediately understands the plain English version, and it takes them 3 to 4 times to understand the technical version. So how is that, a more effective means of communication? I don't think it is, right?